Hi there. So I'm going to talk about section 5.2 right now. I'm going to be referring to certain pages in the book that are really important that you reference and that you have on hand in order to do these. This section does contain a fair number of formulas, but as with this entire course, there's nothing that you need to memorize. You just need to know when and how to use these formulas. All right, and last but not least, I strongly suggest that you work through the examples in the textbook as well. So when I talk about each of these sections, I am making hopefully the safe assumption that you are also reading through the textbook as well, because the point of these videos is just to do an overview. All right, so in section 5.2, I'm going to be discussing angles. Angles are essential in order to do any trigonometry. So when we talk about an angle, essentially what we're doing is we're looking at the rotation between two line segments. So for example, if I take an entire circle and I want to talk about the angle, well, the measure of an angle, which we usually call theta, is the measurement starting at what we call the initial side to what we call the terminal side. You'll notice that I'm starting here on the right and I'm moving counterclockwise. This is not a fluke. This is how we do this. So the key thing that I want to emphasize is that the rotation or angle is between two line segments, starting at what we call the initial side and then moving to the terminal side. Okay, this is a rotational measure. It is not a linear measure, and I will contrast those soon enough. All right, so if we are talking about a circle and the like, we know that one full rotation is 360 degrees. And therefore, so one rotation is 360 degrees. And therefore, 1 degree is essentially 1/360 of a circle. Now, when we talk about angles in our Cartesian coordinate system, our positive x-axis is always our initial side, and we always move counterclockwise. So our standard position is to move counterclockwise. Now, the thing about circles is as follows. If I want to talk about, say, this angle right here, suppose I'm going to say that it's a 30-degree angle. I'm just going to say right now, this is clearly not drawn to scale. It looks already more like 45. But anyhow, I can start here on the initial side, go to the terminal side, and I've gone 30 degrees. But I can also go around the circle and then stop right there. Notice I have the same initial side and the same terminal side, but I've gone around the circle once and then ended up at the same point. When we have these things, they're called coterminal angles. Essentially, they have the same starting point and the same ending point. But for example, with this example that I did right here, well, I've gone 360 degrees once around, and then I've gone an additional 30 degrees. So we would say that's 390 degrees. In other words, we would say that 30 degrees and 390 degrees are coterminal angles. This is a very important concept that we talk about. Okay, so what if I wanted you to find an angle between 0 and 360 degrees, in other words, just one rotation around my circle, that's coterminal with 685 degrees. Okay, Well, we know when we go once around the circle, we've gone 360 degrees. So when you want to find an angle that's coterminal and this number is greater than 360, what you do is you take that degree measure, you subtract off 360 degrees, and what we're going to get is 325 degrees. So if I wanted to somehow indicate this on my circle, on my Cartesian coordinate plane, I go one full time, that's 360 degrees. And then I'm going to go an additional 325 degrees. So it's something like there. And that's my angle theta. Now, just like with your number line, if here is 0, we have a positive direction and we have a negative direction. The same thing with circles, okay? We can go clockwise, but when we go clockwise, our angles have a negative measure. So for example, I can talk about going negative 30 degrees. It just means here's my initial side and I'm going in a clockwise direction of 30 degrees. Okay, so when you see a negative angle, it just means that you're going clockwise as opposed to counterclockwise. So if I wanted to talk about an angle that's coterminal with, say, negative 1,746 degrees, well, that negative just tells me that I'm going clockwise. Okay, now, whenever you want to find an angle that's coterminal, you always want it, but if you're in degree mode, between 0 degrees and 360 degrees. So we always want to think of it as coterminal with an angle in the positive direction. Well, how do we handle this? Well, what you can do in order to find the angle that's coterminal with negative 1,746 degrees is you could say, well, we want to subtract off or add on, if you will, since this is negative, multiples of 360 to find out how many excess times we've gone around the circle. I always think of this as like a cat or a dog. You know how when you have a cat or a dog that's laying down and they want to go curl up in a ball, sometimes they go around and around and around and around and around and then finally plop down, and you think to yourself, well, why didn't they just plop down in the first place? That's the way I think of coterminal angles. So we can go once around the circle in this negative direction, which is 360 degrees. And we can keep doing that. And I claim if you keep adding on 360 degrees, you're going to have to do it multiple times. We're going around this circle many, many times. You're going to end up in the first quadrant with a 54-degree angle. Okay. All right. Now, in terms of getting used to doing the trigonometry, I simply cannot stress it enough. You want to look at page 349 in your textbook because there's some very, very, very common angles. And these are things that even if you don't want to memorize them, you're going to, because we're just going to be using them often enough. Okay. So here's 0 degrees. This is 90, 180, 270. And then here we're back at 360, and you can keep going around and around and around. Okay. But our most important angles, if you will, that we tend to look at are 30-degree angles, 45-degree angles, and 60-degree angles. But also these 4 are also very common. Notice each of these are in my first quadrant. So here's my 30 degrees, here's my 45 degrees, and finally, here's my 60 degrees. But we're also going to want to talk about these in other quadrants as well. So for example, I want you to be able to know where a 120-degree angle is. We know it's between 90 and 180. So we can say that's definitely a second quadrant angle. And here is 120 degrees. Okay. Again, it's always from our initial side to our terminal side. Another very common angle that we look at, for example, is as follows. What if I wanted to look at a 315-degree angle? Well, I know that 315 degrees is between 270 and 360. So I know that that's a fourth quadrant angle, and that's going to give me 315 degrees. All right. So again, finding the angles on a circle are really important. Let's just do one more. What if I want us to locate negative 135 degrees? Okay. Now, if you want to think about negative angles, you could say, well, this is 0 degrees. If I go down here, that's the same as negative 90 degrees. Again, I'm just going clockwise, sorry. And then this is the same as negative 180. This is the same as negative 270, etc. So if I was wanting to go negative 135 degrees, I know that that's between negative 90 and negative 180. So this angle right here would be negative 135 degrees. Now, if we wanted to know what angle is coterminal with negative 135, well, what I would say is we want to find this portion right here. Notice it has the same initial side and same terminal side. We're just going counterclockwise as opposed to clockwise. So what I would do is just take 360 minus 135 because the whole thing is 360. I'm not interested in this 135. And I would say it's a 225-degree angle. Notice that that makes entire sense because a positive 225 degrees is also a third quadrant angle because it's between 180 and 270. So degrees are a really common way of looking at angles. And in fact, that's what we're most familiar with. But there is another unit of measure of angles that's more common, that's based upon the distance around a circle. Okay. And this is used a lot in calculus. So it's something that you're going to want to get used to, is looking at angles measured in what we call radians. Okay. So one of the things that I want to mention to you is as follows. And the cool thing about measuring things in radians is it's a unitless measure. And that can actually be extraordinarily helpful with things. Okay. So if I have a circle, pretend that's a circle. We know that the distance around a circle is called our circumference. Okay. Well, let's say that this is a circle with radius r. Okay. We know that the radius is the same here. Well, when we talk about this distance here, this is called our arc length. We call that S. And what we say is it's the length of the arc, S, along a circle of radius r, subtended by an angle theta. In other words, when we talk about the arc length, it's the portion of the circumference of the circle between our initial side and our terminal side. This is a really important concept. Well, if we want to talk about that, we know the formula for the circumference of a circle is 2 pi r. Sorry, I have a kitty who's wanting to come. This is my little kitty cat, and he's wanting to come and help. All right. So if we look at the ratio of the circumference of a circle to the radius, it's always going to be the same. Notice It's the ratio of the circumference of a circle to the radius. It's always 2 pi. So the whole point of this is regardless of the ratio, regardless of the radius, the ratio of the circumference of a circle to the radius is always the same. It only depends upon the angle. Okay, so when we talk about the radian measure, of an angle, it's the ratio of the length of the circular arc, subtended by the angle to the radius. In other words, we're looking at the arc length over the radius, and that is equal to our radian measure of the circle. One thing that I want you to note is if my radius is equal to 1, if my radius is equal to 1, then the radian measure, S over R, is equal to the arc length. This is only true in a circle of radius 1, but it's super duper important. And again, I just want to really emphasize that since the radian measure is a ratio of 2 lengths, it's unitless. The units cancel each other out. All right, so of course, the magic question is, what is the relationship between radian measure and degree measure? Because we all think in terms of degrees, and so we want something to relate it to, okay? Well, we know 1 time around a circle is 360 degrees. That's in terms of our degree measure. We know that since we're talking about the arc length around the circle when we're doing radians, well, that's the same as 2 pi r. Okay, that's our distance around the circle. Now, we like to consider our radius to be equal to 1. Again, our radius can be anything because it's just not relevant to our computations. So what we say is that 360 degrees is the same as 2 pi radians. Okay, and this is the crux of us doing these conversions between. Okay, one thing we can do is we can divide both sides by 2 and say that pi radians is 180 degrees. Okay, this gives us our conversion. Okay, because in that way, we can divide both sides, for example, by 180 degrees, and we could say that 1 degree is pi over 180 radians. Or similarly, we can divide both sides by pi, and we could say that 180 over pi is equal to 1 radian. Okay, this gives us our conversions. But before I go any further, we have this to be 0, 90, 180, 270, 360. If we wanted to put that in terms of radians, which is something that's super important to kind of start wrapping your mind around. Well, 0 is 0. 90 degrees is pi over 2 radians. 180 degrees is pi. And that makes total sense, right? That's half. You'll see that this is 3 pi over 2, and this is 2 pi. Okay, So one of the things that I want to say that I cannot emphasize enough is practice doing these conversions. So for example, 30 degrees, totally common angle. How do we convert that into radians? Well, in order to go from degrees to radians, what you do is you multiply. So degrees to radians, you multiply by pi over 180. So we say that's times pi over 180. 30 goes into 180 6 times. So we say that 30 degrees is the same as pi over 6 radians. 60 degrees, well, multiply that by pi over 180, and you're going to see that that's pi over 3 radians. And I understand that this is uncomfortable at first. It takes practice, and I just encourage you to play around. The familiarity and the importance of this just simply cannot be overemphasized. 45 degrees, again, change it to radians, multiply by pi over 180, and you're going to get pi over 4 radians. All right, so that is going from radians to, or excuse me, from degrees to radians. Now what I'm going to do is go from radians to degrees. So for example, what if I have 5 pi over 6? Okay, that's in radians, and you often know that you're in radians because you have the pi, although you don't always need to have that. How do you convert from radians to degrees? Well, you do just the opposite. You multiply by 180 over pi. So if I do that, I take 180 over pi. My pi's cancel. 6 goes into 180 3 times, and we're going to get 150 degrees. Now, just like it's important to know that, okay, we know 150 degrees is in our second quadrant. If this is pi over 2 radians and this is pi radians, what's the easiest way of locating where 5 pi over 6 radians is without having to convert it to degrees? What I would suggest is get a common denominator. We know that pi is 6 pi over 6. We know that half of that is 3 pi over 6. And I think you'll grant me that 5 pi over 6 is between 3 pi over 6 and 6 pi over 6. So that's another way that you can check that. All right. So another one that I want to do is as follows. What if I want to look at negative 3 pi over 2? Okay, the negative tells me that I'm going in the clockwise direction. And this is pi over 2, pi, 3 pi over 2, and then again at 2 pi. Well, we know that positive 3 pi over 2 is down here. So if I want to go negative 3 pi over 2, sorry about that, it just means that we're right here. So we would say that pi over 2 is coterminal with that negative 3 pi over 2. All right, please, my friends, play with this a lot, okay? Let's do one more coterminal guy. What if I want to find the angle between 0 and 2 pi, in other words, going in the counterclockwise direction, that's coterminal with, say, 26 pi over 9, okay? Well, we know we're going in the positive direction, okay? We know we're going counterclockwise. So we know that going one full time around is 2 pi. Again, I suggest you do these denominators here, okay? So, for example, if we have a denominator of 9, this is 9 pi over 9, right? This is 9 pi over 18. Right, because it's half of them, okay? If I go 2 pi, that's the same as 18 pi over 9. So one time around, I've gone 18 pi over 9. So I'm going to subtract that off. And if I take 26 pi over 9 minus 18 pi over 9, I get 8 pi over 9, which is going to be right here. Okay, I know this might seem daunting at first, but just be patient with yourself and allow yourself to practice. This stuff comes with time, and we'll be building it as we proceed through the entire course. All right, so what we've established thus far is that our radian measure is equal to the arc length over the radius. And we can solve it for S. In other words, we can say that the arc length of a circle is equal to the radius times the angle. The key thing is this must be measured in radians, i.e., if your angle's given in degrees, change it to radians. Okay, so let's just practice a couple examples here. What if we have a circle with a radius equal to 7 miles, and we want to find the arc length of that circle that subtends a central angle theta equaling 5 radians. Okay, this is the sweetest situation you can be in because you're already in the radian measure. Notice you want to find the arc length S. Well, that's equal to 7, which is R, times theta, which is 5. So we would say that the arc length is 35 miles. Okay, now let's take another one, but now I'm going to want to find my arc length, but now I'm going to have the radius of my circle be 12 centimeters. And now I'm going to tell you that my angle is 120 degrees. Okay, so step 1, change this angle measure from degrees to radians. Okay, and I'm doing this intentionally so we get the practice. The way you change from degrees to radians is you multiply by pi over 180. Those cancel. 6 goes into 12 twice, into 18 3 times. So 120 degrees is 2 pi over 3 radians. Okay. You will learn this whether you want to or not, because this is just an angle that comes up a lot. So now we can do the computation. We have S is equal to R theta. So we take my radius is 12. My angle is 2 pi over 3. And so we get 8 pi centimeters. All right. Now, if you wanted to enter a decimal answer, for example, in the online homework, you would just literally take 8 times pi in your calculator. All right. So similar but slightly different. Is this example. Suppose I tell you that my radius is equal to 6 feet. I want to find the angle in degree mode, and I'm only doing it in degree mode so that we get the practice with our conversions, that would subtend an arc length of 2 feet. Well, notice we want to find the angle. We certainly have that. So the angle is equal to S over R, which notice is 2 feet over 6 feet. My feet cancel, which sounds rather painful. And so we get 1/3 radians. Well, cool. What is 1/3 radians in degrees? Well, remember the way you go from radians to degrees is as follows. You multiply by 180 over pi. So I have 1/3 times 180 over pi. So we're going to get 60 over pi degrees, which if you put this in your calculator, you're going to get about 28.6749 degrees. All right, so thus far, important connections to make is to go from degrees to radians, you multiply by pi over 180. To go from radians to degrees, you multiply by 180 over pi, and then the relationship between the arc length, the radius, and the angle is as follows. Notice this theta, though, in order to use that equivalence, must be in terms of radians. All right, we can also use this formula to find the area of a sector of a circle. So again, let's pretend this is a decently drawn circle centered at my origin. Suppose I wanted to find, oh geez, sorry, my cat just hit something here. Let me do this. Okay, now we're back. All right, so now what I would like to do, let me just get out of that for a second. No. Sorry about this. Let me go back to, okay. All right. So sorry about that. It's the trouble with doing these things at home. Anyhow, if we wanted to find the area of a sector of a circle, well, we know the area of a circle is pi r squared. But if we want to just find the area of a sector of a circle, then what we're going to say is, well, we only want the area, that the portion that's cut by this angle theta. Okay. In other words, we just want a fraction of the circle. So essentially, the fraction of the circle that we want is the fraction of that angle over the entire circle of pi r squared. Okay. Again, it's just this fraction of the circle. Well, you can write that as theta pi r squared over 2 pi. Notice your pi's cancel. So what we have is that the area of the sector of a circle is 1/2 theta r squared. Again, it's key to note that that's in radians. So just to practice another example of this, suppose I tell you that we want to find the area of the sector that's cut by an angle of 45 degrees. This is one of our very, very common angles. If the radius is equal to 6 centimeters. Okay, well, first thing we have to do is we have to convert this into radians. This is one of those you're going to know whether you like it or not, because it comes up so frequently. So we multiply by pi over 180. And what you're going to get is 45 goes into 184 times. So this is pi over 4 radians. So the area is 1/2 times pi over 4 times 6 squared. And if you do this computation, what you're going to see is that you're going to get about 14.1372 square centimeters. Okay, notice I used the estimate for pi in my calculations. All right, so the last topic, and I know this seems like a lot, really the most important thing you're going to get out of this section is the conversions between radians and degrees. But these other ideas are really, really kind of amusing as well. Okay, so what I want to contrast now is as follows. All right, so suppose this is R, this is S, and this is theta. Okay, when we measure our speed, for example, when driving, that's a linear speed. So if I wanted to know the speed when driving, this would be like our linear speed. And so we call that, for example, our linear velocity. When traveling along a circle, that's called our angular velocity, okay? Or our rotational speed. Clearly, this is a longer distance than that distance straight between those 2 points, okay? So this is our rotational speed or our angular velocity, and this is our linear velocity. Now, there's some formulas that we have here. Again, this isn't going to be a major portion of the course at all, but I think that these do lead to some amusing computations that we can do. But the formulas that you're going to use in this particular section are as follows. Our angular velocity, which we kind of call that fancy W, is equal to theta. This is in radians, over t, whatever our unit of time is. Okay, notice this makes sense in terms of our arc length. And notice since it's a speed, obviously we need time to come into it. For our linear velocity, we say that that's the S over t. Okay, notice here, in other words, there's that r theta. Now, what I want to do is show you the relationship between the linear velocity and the angular velocity. We know S is equal to r theta. So I can rewrite my linear velocity as r theta over t just by substituting that in. And we know from our angular velocity that we can write theta is equal to the angular velocity times t. So in place of my theta, I could say that's r times w times t over t. In other words, our linear velocity is equal to the radius times the angular velocity. And again, the key thing to keep in mind is that this must be measured in radians. All right, I'm gonna do two kind of cute little examples here, just so that you get the hang of it. All right, so the first one that I'm going to do is actually one of them that's out of the book. I'll put the book down here. I don't know if you're actually going to be able to see it very clearly. You can look at it online for sure. But what the problem reads is as follows. We have a CD that has a diameter of 120 millimeters, okay? And when playing audio, the angular speed varies to keep the linear speed constant where the disc is being read. When reading along the outer edge of the disc, the angular speed we're given is about 200 RPM, revolutions per minute. And what we want to do here is find the linear speed. All right, so what do we have? What we have thus far is as follows. We're given that the diameter is 120 millimeters. We don't think about things here in terms of diameter. We want to talk about the radius. So our radius is going to be 60 millimeters because that's half our diameter. Okay. Well, notice we want to find our linear speed and we're given our angular speed. Okay, we know the relationship between our linear speed and our angular speed is this. And we actually already have this value right here. The issue is we need our angular speed in terms of radians per minute, not revolutions per minute. So the first thing we need to do is we need to convert 200 RPM to radians per minute. Well, 200 rotations per minute. We like the minute. We want to get rid of the rotations. So one rotation, we know one full time around a circle is 2 pi radians. Notice that will get us into the correct units here. In other words, our angular speed is 400 pi radians per minute. So to find our linear speed, we take 60 times 400 pi. In other words, 24,000 pi millimeters per minute. And if you want to get rid of the pi, you can take 24,000 times pi and get 75,398.22 millimeters per minute. All right, one more example that I think is a kind of a cute example we're going to look at is number 31 here. And what that says is you're standing on the equator of the Earth with a radius of 3,960 miles. What is your linear speed and what is your angular speed? Okay, so for this one, we have R is 3,960 miles. And we want to find our speed in hours. Okay, well, we go around a full revolution around in 1 day. 1 day is 24 hours. So in 1 hour, what have we done? We've gone 1/24 of the total distance around the circle. In other words, our angular speed is 1/12 pi radians per hour, right? One full time around is 2 pi radians in 1 hour. Notice the radius is not relevant here, as we pointed out before when we talk about our radians. Okay, so we've gone 1/24 of that 2 pi. Well, now that I have my angular velocity, to find my linear, I just take that times the radius. And we're going to get about 1036.73 miles per hour. All right. I hope this was helpful. I encourage you to work through these examples again, and I also encourage you to work through the examples in the book. All righty.